Green, who was scheduled to give the talk on machinery standards, is lost his voice actually, and he's not feeling that well. So he asked me whether I could offer something as a substitute. So here we are with a presentation on LOPA considerations. Let me confess, a little bit thrown together. This was literally put together yesterday, and so there's some hand sketches in here and the like. But hopefully you'll find it a coherent and interesting presentation. You'll have to let me know, and then if I need to make some tweaks, so be it. So this is the territory I plan to cover. First of all, look at how LOPA is used, what are the correct expectations of what you might derive from LOPA. Protection layer timing is a key consideration that I'm going to do a little demonstration for. Mitigation layers, which are after the event has been realized. If the hazard event is actually realized, these mitigation layers can act to reduce the consequence. So they won't prevent the event happening, but they can reduce the consequence. And there's a question of how might we manage that within LOPA. I'm going to talk a little bit about enabling conditions and talk quite a bit about conditional modifiers associated with release hazards, particularly over occupancy. There's a deal of confusion over occupancy claims, so I shall be exploring that in some detail, and then also consider avoidance and probability of ignition. So that's in outline where we're headed. In terms of uses, certainly we use LOPA, of course, for SIL determination purposes, but we have to recognize that it is certainly not an exact science. Nothing within functional safety is an exact science. The numbers always remain highly uncertain, not only in failure rates, but demand rates and the like. Even the targets can be uncertain. So the day you start to believe the numbers is the day you've lost the plot, really. That's not to say that they aren't useful, but we have to recognize what they represent. At best, a LOPA study might offer a half order magnitude in terms of accuracy, so it could be out by at least a factor 3 either way. Yeah, we're in that sort of territory. More typically, it might well be an order of magnitude, so a factor 10 either way is entirely possible. And in that respect, a LOPA should only be regarded as establishing ranging shots for the analysis of risk, for evaluating the risk in any given scenario. It remains useful in that respect, of course, because it does allow us to perform these sensitivity checks. How sensitive is the reported outcome to the assumptions that we choose to make, or the judgments we choose to make in our analysis? And it does allow us to explore the considerations arising in any given scenario. So all very useful, and perhaps the key point of a LOPA is to allow those sort of explorations. Fundamental to all of this, of course, is the actual SIL target that we're trying to achieve. And I could spend a whole presentation just exploring tolerable risk targets and their specification, because it is an area where there is a lot of confusion. One of the first confusions that I often see is that because people have met the broadly acceptable threshold that the HSE point to of 10 to the -6 per year for individual fatality, people assume that that is the appropriate target for a fatal hazard, and that isn't necessarily the case. The implication of the broadly acceptable threshold is that if you establish the risk is below that threshold, then you don't need to look at it further. It's not to say that the broadly acceptable threshold must be the target. And for most process hazards, certainly, a target at 10 to the minus 6 would typically be well beyond the alarm consideration. Not going to explore that in detail, but at least I've alerted you to that possible confusion, possible difficulty there. If you make the targets that much more ambitious than is really warranted, of course, you will inflate the sill targets for all your protection, and with that may come a world of grief and pain in terms of the engineering that in truth is not really warranted. That's the difficulty. I have known clients say, oh, we're going to do even better than that. We're going to go for 10 to the minus 7. We're 10 times better than everybody else. And it just brings a world of pain and grief. So not to be done on a whim. Okay, so let's get into LOPA territory proper. I want to explore the timing issue first of all. And for these purposes, I borrowed this example from this paper you can see referenced at the bottom from Alan King, which highlighted these concerns. So I'm using the same calculations that he presented in his paper to illustrate the point. So in this particular application, we have this flare knockout drum, which if everything fails, could potentially fail catastrophically. So we have an overpressure protection function, 2 out of 3 pressure sensors that will close this valve, although that's not in truth part of the SIF, and open this trip valve B to vent the vessel to flare. That's the essential action of the SIF that's contemplated here. There are also 2 mechanical relief provisions here, bursting disc and a pin rupture valve, which is again another mechanical relief device, which has a pin that buckles to allow the closure member to open and relieve the pressure. So 2 independent protection layer provisions there. Okay, so that's the scenario. We're concerned about an overpressure in this drum. And at this point, I'm going to switch, if I can get this right. Hopefully everybody can see now a LOPA analysis screen. For this purpose, I'm using the SysSuite software. So this is provides a suite of tools for managing the safety life cycle, but I'm interested in this particular LOPA, which is teed up to explore the knockout drum scenario. So you can see the scenario is knockout drum. That's the hazard event. The consequences, somewhat flippantly designated very bad. The tolerable risk level is assigned here. These can be nominated by the user, and for this particular exercise, this is assigned a tolerable frequency of 1 e to the minus 6 per year. That's the S6 major category, but they're assigned by the user. And then we have here identified the initiating event frequencies. And there are 3 identified. Too much gas, basically, it's coming in faster than the compressor can handle, leading to an overpressure, and that's 10 times a year. The compressor trips, again, 10 times a year, and the outlet valve could spuriously close, so effectively deadheading the vessel, again causing a pressure rise. Just one point in passing here, if you look at the American guidance for LOPA, they talk about only dealing with 1 cause-consequence pair at a time. I think their concern is that different protection layers can protect against different initiating events, and if you're not careful, that can be confused. But as long as you you're aware of that and make provision for it within the LOPA calculation, in truth, I don't see a problem. So here we have multiple initiating events that we're looking at. Total of 22 a year as things stand. On a more complete record, we'd be entering the justification. You know, there's free text fields here, so we'll be entering the justifications for those entries there. ECP is assigned 1 to all of this. This is the enabling condition probability. Where you would see that used, a typical example would be on a batch plant, where perhaps you only make the hazardous material, the toxic material, whatever it might be, for half the year. So there would be no possibility of a hazard arising for half the year. And so we could assign an enabling condition probability of 0.5 to all of these. So that is another possibility here. Not employed in this example, but the facility is there. In terms of independent protection layers, we have the two that we saw in the drawing, the bursting disc and the rupture pin valve, both of which are assigned a risk reduction factor of 100. In this defense matrix here, we indicate which protection layers defend against which initiating events. And if I hover over the ticks, you can see the combinations declared there. And in this particular example, both independent protection layers defend against all 3 initiating causes. We crunch those numbers and it gives us the demand rate and the hazard event frequency. I've also assigned here an ignition probability as a conditional modifier of 0.2, making no claim for fire suppression, although we'll come back and explore that shortly. Okay, so that reflects the example we were just looking at, and this LOPA study here, in order to meet that tolerable risk target that we specified, identifies that we would need a SIL2 SIF. So the 2 out of 3 pressure trip would need to be engineered to a SIL2 capability and offer a risk reduction of 440. Okay, so that's our first pass analysis. But in terms of the timing, I want to just show you the impact by editing the record. So I'm not changing anything here except for this little switch here, because the key point here in this example is that you would normally expect mechanical relief to be invoked after an instrumented trip. Normally you would expect a pressure trip to arise before your bursting disc blew. And so with this switch, we can specify whether these independent protection layers are invoked before or after the SIF. Is it pre or post the SIF operation? So I've now switched those to indicate that they would be expected to operate after the SIF proper. I can save that. And having changed nothing else, you can see that the requirement now is SIL1, not SIL2. And that is because we've now identified that the SIF, the instrumented protection, would be operating in high demand mode. And so now we have a specification of probability of failure per hour rather than the PFD that we had with the low demand SIL2 specification. If I flip back to my presentation. Okay, so this slide's a little busy, but hopefully this will explain why there's that counterintuitive possibility of a SIL1 requirement for this particular application. If we look at the low demand possibilities, first of all, and we imagine a dangerous failure rate for the SIF of 0.04 per year with a 1-year test interval, then most people will be familiar with the routine half lambda dangerous test interval equation here, which gives us the PFD average of 0.02. With a demand rate of 0.1, that would give us a event frequency of 0.002. And we've got a logarithmic plot here of hazard event frequency against demand rate, and you can see that we have this line here that corresponds with that equation. If we switch to the example where it's a high demand rate, but with the same SIF capability, then we end up with at 100 demands per year, the implication would be that the demand rate was, the hazard event frequency rather, would be at twice per year. But in truth, when you consider that the SIF itself is only going to fail at 0.04 per year, you can see that that puts a limit on the hazardous event frequency. So we have this switch at this break point, which is nominally 1 demand per year. And in the 61508, 61511, that's the break point at which we switch from a specification for low demand rate to high demand rate. And you can see in terms of the analysis, that can be highly significant. So not something to be overlooked. Right, now then, so that calculation would be flawed. That would not be relevant for a high demand mode scenario. That's the key point there. Okay, so the next item I want to look at, that's the timing issue explored, and this question of whether the independent protection layers are invoked before or after the proposed safety instrumented function. Let's consider now mitigation, and the classic example is fire suppression. The point about mitigation is that it does nothing to prevent the hazard event occurring, but it potentially reduces the consequence. And if the consequence is reduced in scale, then it becomes more tolerable. And the question arises as how we might handle that. We can define that change in tolerability as a mitigation factor. So, for example, if the consequence you would typically anticipate a fatality as being the consequence, but if the fire suppression was successful, the consequence you might expect to be a severe injury rather than a fatality, then there will be a corresponding change in the tolerability for that consequence. Might be a factor 10 change, for example, which is what I'm going to use in a moment. And in recognition of that, we can calculate the average risk reduction factor required across all outcomes, depending on whether the mitigation is successful or not. And by way of example, let's switch back to my example. I'm going to, first of all, restore these to as they were, to just put us back on a level playing field. So we see the original SIL 2 440. Now, given this example, that is not a, selecting them in that way is not valid for this example, but it allows me to illustrate the impact of mitigation. So that's why I've done that. So I shall now edit this again. And the only change I'm going to make this time is that I'm going to introduce fire suppression. No claim was made for it previously, but I'm now going to say that 9 times out of 10, the fire suppression would be successful. Okay, so the probability of it failing will be 0.1. And if I introduce a mitigation factor of 10, which means that if the mitigation is successful, as we're expecting 9 times out of 10, that would mean that the consequence was 10 times more tolerable. Okay, those are the only changes I'm going to make. Save that, and you can see we're back now at SIL 1, still low demand, but now the risk reduction factor has fallen, requirement has fallen from 440 to 83.6. You might wonder what the little DF is. That indicates that this is a dynamic field. In SysSuite, if you revise an upstream record, once it's been checked and approved, all the downstream records that are using that information will automatically update. So there's an automatic propagation through the system, which can be a great labor saver. If you've got 50 records all using the same failure rate data, which you then revise, you don't have to go and revise all 50 records. That automatically happens through the data propagation. So there we are. That's the mitigation aspect explored. Let me turn to my presentation. So conditional modifiers now I want to explore. And one that we very commonly meet is occupancy. And this is classically addressed by considering the percentage of time for which somebody would be exposed. What percentage of their time would they be in the hazard zone is the classical simple calculation that is often used, and which you see declared in the text on this sort of topic. Here's my little hand sketch to indicate a possible work pattern where somebody is spending 20% of their time. I've not indicated any units here. It doesn't really matter whether these are hours or days, minutes. You take the point that there's a notional periodicity to their attendance, and that in that continuing period, 20% of the time, somebody is exposed to the hazard. And so the simple answer is to put in a conditional modifier of 0.2 into your LOPA. But there are a number of traps for the unwary with this. What if that 20% is, for example, truck loading activity? And if the hazard is associated with the truck loading, then the point is that while the hazard is potentially present, so is the operator. So in that respect, the occupancy is not 0.2, it's not 20%, it's 100%, because there is somebody in attendance whenever the hazard potential exists. So this simple percentage of time spent in the hazard zone only works for what I'm here calling latent hazards. Latent typically being flammable material releases or vapor clouds or pools, which only present a hazard to personnel in the event that they subsequently find a source of ignition. The moment they find a source of ignition, then there's an immediate consequence, typically through the fire or the blast or whatever it may be, and there's no real avoiding it at that point. So this simple basis, which is so very often employed, only really works under those conditions. So if it is an attended operation which presents the hazard, for example, the tanker loading, then occupancy cannot be claimed as a conditional modifier. It would in fact be 100%. Another example is with pedestrian exposure. I met this circumstance with a client just recently, where pedestrians were walking through a potential hazard zone. Now, the hazard would only arise at very infrequently, hundreds of thousands of years, whatever it might be. And they would only transit the hazard zone for 10 seconds was the estimate. But that 10-second exposure, well, potential exposure, would arise quite frequently. Let's say every half hour somebody would walk through the area and be exposed for that 10 seconds. Now, if you take the 10 seconds as a proportion of the time, just doing the simple percentage calculation, you end up with a very small number, and then you could plug that in as a conditional modifier, but that would be a complete fraud. If you consider that the hazard, let's say the hazard is present for 1 hour, because the hazard persists. It's not a transient thing. It sits there for 1 hour potentially. If somebody passes through that area every half an hour, although they're only exposed for the 10 seconds, you're guaranteed that when that hazard arises, because it persists for an hour, somebody will be exposed. It becomes a certainty. So in such examples, we cannot claim occupancy as a conditional modifier. It becomes, in fact, a certainty, and it becomes 100% again. Another possibility is that people are dispatched to the plant to investigate the circumstances, typically in response to an alarm. They get a high temperature alarm or a high pressure alarm or whatever it may be, and the first reaction is to go onto the plant to investigate what the circumstances are that have given rise to that alarm. But that means that they immediately, potentially, put themselves in harm's way. So if people are likely to attend to investigate, then we can, again, no longer claim occupancy for those individuals. And the other problem is with a potentially persistent hazard rather than a latent hazard. And so that the point here is that although we commonly talk of occupancy, that's not really quite right. More accurately, our interest is in the probability of encountering the hazard if it should arise. A subtle distinction, but an important one nevertheless. And here's my simple explanation of that. We've got the same work pattern as you saw before, but here I've represented a hazard that persists for the period indicated there. And you can see that immediately the occupancy is inevitably 1. It's 100%. There's no claim could be made for such a hazard. We can correct for this by using this equation, which calculates the effective occupancy as a function of the duration of the occupancy, the duration of the hazard over the base period with which the occupancy arises. And by way of an example, if the duration every 24 hours, which becomes my base period, was 2 hours, that's the occupation duration, and the hazard itself was present for 6 hours, then if we plug those numbers into that little equation, the probability of occupancy would be 0.33. Whereas if you'd just looked at the percentage of time that somebody was present, you'd just be using the 2 over 24, and it would be 0.08. So you can see you get a very different answer. So an important consideration. For these release hazards, certainly there is the possibility of gas detection alerting people to the hazard and allowing them to intervene potentially to terminate the hazard earlier than it would be if they weren't alerted. And this little equation allows us to calculate what the effective hazard duration would be. It's simply an average. If the gas detection is not effective, then the hazard duration would be unmodified. So that's the HD there. If the alarm is successful, then the duration would be whatever we estimated was the time for the alarm response to terminate the hazard. So if we imagine the probability of gas detection alarm being successful was 0.1, which is typically the sort of assumption you might make. 1 over 0.1, that gives us the 10 minus 1. So we're saying 9 times out of 10, basically, the hazard would terminate after this period. 1 time in 10, it would not be terminated early, and it would be the full hazard duration. And then we're simply averaging that. So that allows us to compute the effective hazard duration. And here's my little summary table. This is from the new edition of my book that I'm working on. So depending on the hazard type, we can categorize it as shown here. So if it's a pool or a jet fire, so essentially a liquid release, a latent hazard, then we can claim occupancy on the simple basis of the time spent in the hazardous area. If the release is apparent, so it would be self-evident to anybody that was in the area or approaching the area, then we can make a claim for avoidance. You know, in the expectation that they would recognize the hazard and either terminate it or remove themselves from the hazard zone. If we flip over to the other side and consider a vapor release now and the potential for a flash fire or an explosion, again, this would be a latent hazard. It would only, the actual consequences would only arise if there was a subsequent source of ignition. So that's why it's described here as latent. So on the same basis, we can potentially make a claim for occupancy. If the release again is apparent, perhaps because of the odor, or perhaps there is, if you encounter the vapor cloud, you're going to suffer respiratory distress or whatever, then yes, we can make a claim for avoidance. But if the hazard potential would not be apparent to the operator or whoever it is that is approaching that zone, then of course we couldn't make a claim for avoidance. If the hazard is rather than explosive, is toxic or asphyxiating, then I'm making the distinction here between a transient, relatively short-lived hazard duration and a persistent one. If it's persistent, as per my little sketch, then no claim of occupancy can be made, because the expectation is that at some point somebody will encounter that hazard. If it's transient, then we can make a claim for occupancy, provided we look at the probability of somebody encountering the hazard. So now we have to consider not only the hazard duration, but also the occupancy duration and the periodicity with which this occurs. So you're looking for the probability of coincidence of the hazard being present and somebody occupying the hazardous area. Similar considerations again with avoidance for both of those. If the hazard is immediately disabling or would not be apparent, it's invisible and got no smell, or it would not give out immediately, that's nitrogen release perhaps, then you could make no claim for avoidance. But if it's not immediately disabling and would be apparent because of the odor, because of respiratory distress or whatever it might be, then potentially an avoidance claim would be a possibility, would be a legitimate claim that you could make as a conditional modifier. Probability of ignition then can be a fraught area. There are a variety of papers and books and topics on this, but remembering that we're tackling LOPA here, so we have to accept that there is a high degree of uncertainty in all the numbers that we use. So there's really no point stressing over the third decimal place in any of this. But we need to assign some sensible looking figure to the probability of ignition. So this is my proposal, which has been informed by, in particular, not exclusively these, but there's this HSE research report and the Energy Institute Guide for Hazardous Area Classification, EI15. If the release is confined to a zoned area, then you would hope that there will be a correspondingly low probability of ignition, or else why we're bothering with the whole zoning exercise. That's the idea of it, is that we manage the area, manage the assets, and so in accordance with EI15 for zone 2, they on that basis alone assign an ignition probability of 0.01. If there is a strong source of ignition, such as a fired heater or a boiler house or a flare or anything of that ilk, then we must assume, of course, that the ignition is certain. It might not be absolutely certain in practice, but as a matter of prudence, you would have to assume that the ignition would be certain if there was a likelihood of any release extending to any such strong source. If the release extended beyond the zoned area, but the site was it was still a controlled area, so it's a site where you don't allow smoking materials on site and only diesel engine vehicles, etc., and you only allow hot work under a permit, all these sort of routine sort of provisions, then you may, I'm suggesting, use a base ignition probability of 0.1, and then you would modify that in recognition that if the release is 2C or temperature class T5 or 6, so a more easily ignited release than otherwise, then adding a 0.1 probability to that base, so in together that would constitute 0.2. If the release extended to areas, switch rooms, substations where there were supplies being switched, another 0.2. If it extended to an area where there was high traffic or a high level of work activity, another 0.2 there. If the release extended off-site into an urban or industrial area, the starting point is 0.5 with these modifiers again as appropriate. Implicit in these numbers is a degree of averaging, because a lot of this would be sensitive, of course, to whether the release occurred during the day when people are around or at night when not so many people are around. So that is implicit in this figure here. So there we are. There's hopefully people will be satisfied this is a rational basis to assign these numbers, which offers a degree of proportionality in recognition of the nature of the areas to which the release may extend. There we are, gentlemen. I think that's all the territory I was planning to cover. A famous quotation here from Isambard Brunel, when he was told that one of his bridges had fallen down. I'm glad to hear it. I was about to build 20 more like it. These are the timber bridges, railway bridges on the Great Western Railway. I'm about to, I'm working on the next edition of my book, and so a lot of this material will be incorporated in that. So if somebody sees some flaws in what I've presented here, the sooner I know about it, the better. So I echo Brunel's sentiment in that regard. Okay, some contact details on the screen for you now, but at this point, I think we'll flip into questions and answers.